Okay, so part 3, I think I have these all filled in, so this should maybe go a little bit quicker too. Again, pause this video at any point in time to get yourself caught up. So now what we're going to do, the last part of chapter 16, is connecting all of these random variables to the normal model. Because remember, your area under the curve represents your probabilities, right? We looked at all those different types of probability distribution histograms. So your area underneath the normal model represents your probabilities, as long as the data that you're representing can be represented using the normal model. So we need to be able to assume that the data set that we're looking at is roughly normal. Because if it's not, then we can't use the normal model to come up with our probabilities. We have to use other methods, which is beyond our course. So here are some actual problems where it comes into a little bit of real world use. So a college uses SAT scores as one of the criterion for admission. Experience has shown that the distribution of scores among its entire population of applicants is as shown in the table below. What are the mean and standard deviation of the total SAT score among students applying to this college? So we're finding the expected value of math plus the expected value of verbal. Right, so that means we just add the 625 plus the 590 to get an expected value of both scores being around 1,215, right? So now, standard deviation of math plus verbal. Well, we can't really find this because math scores and verbal scores for these students are not likely to be independent. If you're good at one, you're probably going to be pretty good at the other one. If you're not so good at one, you're probably not going to be so good at the other one, right? Those who score high in one probably are scoring higher than others in the other one. Not the case every single time, right? But I would say that one does affect the other. So let's go to a new concept where we might have independent events. So bicycles arrive at a bike shop in boxes. The means and standard deviations for the setup phases are given in the table below in minutes. A customer decides to buy a bike like one of the display models, but wants a different color. The shop has one still in the box, and the manager says that they can have it ready in half an hour. Find the probability that they can get the bike set up and ready to go as promised. So based on past experience, the shop manager makes the following assumptions. The times for the 3 setup phases are independent. Okay, so that means one does not affect the next. So you do one, get it done, does not affect the next process or the next phase. So this means we can then find combined standard deviation. And the time for each phase are approximately normally distributed. Okay, so we're going to start talking about conditions as we move to sampling distributions. So these are kind of some conditions that we need to check before we can actually move on to doing the math. All right, so let's go ahead and find the mean. So how do we find the mean? The expected value of unpacking plus assembling plus tuning. Well, we just add all our means together, right? So that gets us 38.6 minutes. Okay. We want to know what's the probability that they're going to get the bike set up and ready to go in half an hour. So we want the total time of unpacking, assembling, and tuning to be less than or equal to 30 minutes. So we found the mean. Now we need to be able to find the standard deviation. So standard deviation of unpacking plus assembly plus tuning is equal to the square root of my standard deviation squared of the 1 plus the standard deviation squared plus standard deviation squared, right? So 0.7 squared plus 2.4 squared plus 2.7 squared, which gets us 3.68 minutes is my standard deviation. So is it looking pretty likely? I don't know. If the average time is 38.6 minutes with a plus or minus of 3.68, if we just think about it, if I do 38.6, subtract one standard deviation away, that puts me at 34.92. If I subtract another standard deviation, so now I'm 2 standard deviations, I'm at 3.24. So 30 minutes is more than 2 standard deviations away. And what do we say is pretty unusual? Being more than 2 standard deviations away. So I'm going to say that it's probably not going to be a very high probability. But let's go ahead and find it. So we're going to now use a normal model using our combined mean and standard deviation. So there's your notation, right? So n of 3 so n represents my normal model. Here are my parameters, 38.6 and 3.68. Sketch your curve, throw your median straight down in the middle. You don't have to show all the standard deviations. Just put the value that you're looking for. In this case is the 30 minutes. It would be to the left. Okay, shade in the area we're looking for. We want to be able to get it in within 30 minutes. So they probably would Wouldn't mind if it came in shorter than 30 minutes, right? So I'm finding the area underneath the curve to the left of my 30 mark. Always, 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 always standardize. So find your z-score. 30 minus 38.6 all over 3.68 gets me a z-score of negative 2.34, right? So the probability of u plus a plus t is less than 30, right? Here's our notation, is equal to the probability of z less than negative 2.34. And then how do we do this on our calculator? We do a normal CDF, negative 999999999, negative 2.34, which gets you to the 0.0096. So there's less than 1% chance that the bike shop will have the bike ready in under 30 minutes. The manager is being very silly. Okay, so isn't that cool how it all comes together? Every spring at a good old Podunk High School, the Math Honor Society hosts a trash ball tournament. For this tournament, male and female contestants are randomly paired up as teams. The means and standard deviations for the heights and inches of the male and female contestants are given in the table below. Assume that male heights are independent of female heights and that the heights of both the female and male contestants are normally distributed. So I want to know the difference, right, between them. So we want the difference in heights. So we want male minus female to be less than 0. So if male minus female is less than 0, meaning that it's negative, that means my female was taller. Right? Do you have that in your brain? Okay. So let's go ahead and find the expected value. So the expected value of male minus female is 4.5. Okay, so that means that on average the males are 4.5 inches taller. Your standard deviation of m minus f is the square root of your standard deviation squared plus your standard deviation squared. So 3.2 squared plus 2.8 squared square rooted is 4.25. Okay, so there's our mean and there's our standard deviations. Now let's go ahead and, oops, I missed the first part. Find the probability that a female contestant is paired with a shorter male. There we go. So that's why we want to know that if the female was larger, right? Let me write this out for a second. Come to me. So if my male minus my female is negative, the difference is negative, that means that this is the larger number. That means my females are larger. Could you do f minus m is greater than 0? Yeah, you could. Your expected value of f minus m would then be negative 4.5. So when you do your normal model, you would be at negative 4.5 for your middle. But remember, your tail then would be up here as opposed to down here, which is going to be for us. So it would work because it's symmetric. You get the same results. Okay, so here we go. There's my normal model. There's my parameters, name the model, and parameter 4.5, 4.25, throw a 4.5 down the middle. My bar here is at 0, right? Because at 0, they would be exactly the same, but I want less than. So every data point down here, the female is going to be larger than the male. So find your z-score. 0 minus 4.5 over 4.25 is equal to negative 1.06. Here's your notation. I don't know how to get rid of that. There we go. So your probability of male minus f, so male minus female, is less than 0, is the same as your probability that your z-score is less than negative 1.06. Normal CDF, negative 9999999, negative 1.06 gets you 0.1448. So again, always write out your answer in context. So there's a 14.48% chance that a female would get paired with a shorter man. For part B, find the probability that a male contestant is at least 12 inches taller than his female partner. So now we want to find the probability that m minus f is at least 12, right? So 12 or higher. So again, we're going to use the same mean and standard deviation because we're still doing m minus f, so that's unchanged. Now, my point here is at 12, my breaking point is at 12, and I want it to be at least, so I'm going to go higher than 12. So find your z-score for that. 12 minus 4.5 over 4.25 gets you 1.76. Here's your notation, right? You have to get the notation written out. So your probability of m minus f is greater than 12 is the same as your probability that your z-score is greater than 1.76. So here they did the complement of it. I would have just done 1.76 on my calculator to 9999999, which gets you to the 0.0392. There's a 3.92% chance that a man would be at least 12 inches taller than his female match. So for full credit for this type of problem, you need to be able to check your conditions. We need to make sure we have independent events and that both of the events are assumed to be normally distributed. You need to name your model, right? Here's my name of my model. N represents my normal model. Here are my parameters, right? Because those would be a different model if I had different parameters. Draw a picture of the curve. Throw your mean down the middle. Show where our breaking point is. Last problem was at 0. Now we're at 12. Show how you find your z-score. Show your notation. This notation right here is 2 points every single time. So make sure you don't lose those 2 points. The probability of m minus f greater than 12 is the same as your probability of z greater than 1.76. I personally probably would just skip this step and go right to the 0.0392. And then make sure you write out a sentence in context with your final result. Okay, so make sure you do all of those things. All right, that concludes chapter 16. See you guys.